So we were talking this morning about what I think collectively we thought was very important in students' experience of mathematics is that they should experience some of the delight and the awe and the wonder of mathematics so that they understand, even if it doesn't have a really big part in their future lives, but they can understand why other people are really turned on by mathematics. I think that's important, even if they themselves are not going to make it a very important part of their future career. And so the activities that I've chosen today are really, the mathematical content of them is really very low. It's for elementary students. But there is something in it, I think, probably for people who are a lot more mature than that, as in the current audience. So you'll need a piece of paper and a pencil, or a piece of paper and a pen, and I'd like you to draw a grid 2 by 2. And then choose 4 different digits, so no repeats, between 1 and 9, so that doesn't include 0. Okay, everybody happy with that? Okay, so now I've chosen 5, 2, 1 and 9. And then if you look at the way that I've read off, if I read across, I can get 2 two-digit numbers. 5 and 2 makes 52. 1 then 9 makes 19. And then if I read down, I get 5 and 1, which is 51. And 2 and 9, which is 29. So would you like to write the 4 two-digit numbers that come from your square? And then do a bit of mental arithmetic and add them up. And perhaps you'd like to share your answer with the person next to you. See who's got the bigger. Okay, so my total was 151. Did anybody beat 151? Yes? 169? Anything more than 169? 326? Any advance on 326? Do we think 326 is the biggest? If you could have chosen any numbers you like. Okay, do you want to see if you can put some numbers in to make the biggest total that you can possibly get? So draw yourself another grid. Which 4 numbers would you put in and what total would you get? Anybody beat 326? Yep. 348? 358? 358? 368, sorry. Anybody beat 368? What numbers did you choose for 368? 6, 7, 8, and 9. Did everybody choose 6, 7, 8, and 9? Yes, 6, 7. I mean, for us, it's very obvious that the numbers you need to choose, if you're... Okay, thank you. So if it's 4, the 4 biggest single digits are 6, 7, 8, 9. And so you'd obviously put 9 up in the left-hand column, wouldn't you? And why would you put 9 there? Because that's the tens place. So when I make my 4 two-digit numbers, I'll have 90-something across and 90-something down. Yeah? And where would I put the 8? Where would I put the 8? Below the 9? I think some people were saying it should be where the 2 is. Does it matter? Doesn't matter. Why doesn't it matter? Yep. Because it's in the ones place. Oh, is it always in the ones place? It gets to be both. It's going to be a 10 in one of the numbers and it's going to be a unit in the other of the numbers. And similarly, we use 7. So 7 is in the other diagonal. And then the number which is the smallest number is the 6, which goes in the bottom right-hand corner. And when you add those 4 up, they come to 357. Okay, so 357 is the biggest number. By extension, and if you imagine I would be doing this with a class of maybe 7, 8-year-olds, now that they've had a bit of chat about why they're putting numbers in the right place, now if I asked you to choose 4 different numbers to make the smallest number possible, that would be very easy for you. Agreed? Would you like to do that now then? So first of all, it's your choice of the 4 numbers. So what 4 numbers will you choose? 1, 2, 3, 4, okay, which for us is obvious, for children is not necessarily so. And we have to use the reverse logic. So if we want to make the smallest possible number, then the smallest number needs to be in the most important place. So we'll need to have a 1 in the top left-hand corner, 2 and 3 will go in the diagonals, and 4 will go in the place where it makes the least difference. Agreed? And the total is? 81. 81. Okay. Oh, that's interesting. So now, that's fine. We were just exploring. We did ones of your own. Then I asked you if you could find the biggest, asked you if you could find the smallest. We've got a sense of how this works. So now I'm going to ask you if you could put 4 numbers in so that when you add those 4 two-digit numbers, the answer comes to exactly 100. Okay, you've got a sense of how it works. I'm going to give you about 5 minutes. Can you come up with 4 digits, which will give you a sum of 100 exactly? And if you can't manage it exactly, then how close can you get to 100? Give you 5 minutes. Has anybody got 90-something? Yeah, I've got 92. Anybody got closer than 92? 96. Anybody got closer than 96? What about 100? Has anybody got 103, 102? 102? Okay. 101. Getting closer. 95. Sorry? The thing I'm really interested in, whilst you're doing it, is how you know what to do. What's going on in your head when you decide what numbers to put in? Thinking how many more do you need or how many less do you need, and then that has to be interpreted into actually doing something with the numbers.
Some numbers are around 25.
Some numbers are?
Around 25.
Around 25.
So it has to be split between 4 numbers.
Okay. Okay, so you think the 4 numbers have to...
I chose 2 first.
Yeah.
So then I worked with it.
Okay, so you chose one number and then adjusted the others. Okay. Does anybody else have a different strategy? You're not allowed a 0. When they add it up. What, all 4? When you add all 4 up, they have to come to a 0? The unit place should have a 0. Okay, okay. You've got 100. Okay, don't show anybody else for a moment. See if you can find another way of doing it, because there's more than one way. Don't tell me for a minute. Let everybody have a go first. Okay, so wherever you've got to, would you now just share it with somebody who looks friendly, who's sitting near you, and tell them what you did. Tell them why you did what you did, which ones you put in first and why. So you need to make some noise. Okay, so thinking of this from a teacher's point of view, at the beginning when I asked you to put in numbers and add them up, the room was totally silent, wasn't it? Because you were all concentrating and focusing. So somebody walking past my classroom would think, what a brilliant teacher. All her students are quiet and they're all working along. But actually, when I was a principal, I was much more concerned that there should be talk in my classroom. Because one of the things we say in Cambridge Maths and in Enrich is that you can't do maths unless you talk maths. There's such a connection between thinking and speaking that by putting your thoughts into words, it helps to clarify your thinking processes. So that's why I'm very keen that you have a conversation to share your thinking processes with the person next to you. So, do we think it's possible to get 100 then? Lady in the beautiful pink sari. You've got exactly 100? You've got 100? Who else has got 100? Yes, gentleman at the back. Anybody else got 100 exactly? Yes, several. Okay, so would you like to tell us what your 4 numbers are? And could you please write them down, because we need to check he's not cheating, okay? Okay, could you go from top left to top right, bottom left to bottom right? 2, 1, 3, 8. Could you do a quick bit of mental arithmetic and make sure that works? Is he right? Yep, good. Does anybody have anything different? So you have...
I have used 4 numbers.
Yeah.
And 600 something. It is 2318.
2318. So the 1 and the 3 you've swapped over. So I probably wouldn't call that a different solution. I'd call that the same solution. Has anybody got a different solution using any other numbers? Okay, so one of the questions I would leave you with, because I like to leave my classes with some activities that I call simmering activities. Do you use the word simmering? You know, when you have a pan of water and the bubbles are just keeping going, I like to set my students simmering things for them to go away and thinking about. So one of the things I'd like them to do is to go away and see if they can find another way of finding 100. But there's something more interesting than that. So we said that the biggest number we could find was, can anybody remember? 357. And the smallest number we could find was 83. So one of the things I'm interested in was, I chose 100 because 100 is a nice number. But what if I'd said, can you find 4 numbers that add up to 101? Did anybody get 101? Okay, so we know that's definitely true. We can do that. What about 102? Okay, we know 102. This is good. The class is all combining, so we don't all have to do the work. 103. Did anybody get 103? Okay, so it might mean that it's not possible to get 103, or it might mean that we just haven't done it yet. But as a class, I could keep you here for a while, and on this wall over here, I'd give you all post-its, and I'd ask you to see if you could make all the numbers between 83 and 357. Is it possible to make totals of all the numbers in between? And if it is, I would ask the class to work together to show me a solution for each number. And if it's not, I would like to know why it's not possible. Now, I know there are some people in the room who've started using some algebra. Put your hand up if you've started using some algebra. Okay. So I wonder if algebra is going to help you at all in working out whether it is or whether it isn't possible to do all of those sums without having to actually do them. Because that's the beauty of algebra, it allows us to generalize. We don't have to have every specific answer. We can use some algebra to come up with an argument which will show me whether it is true or whether it's not true, no matter what the numbers are that I'm using. So I'm going to leave you with that, because one of the things we do in Enrich is we never tell anybody the answer. And why don't we tell anybody the answer? Because once I've told you the answer, you've lost interest. You may have lost interest anyway. But the point is that if you haven't lost interest, you've now got something to go away and worry about. And that's really important. I want the students in my class to go away and worry about something and make that mathematics their own. So I asked you whether you could find the largest and the smallest. I then said, what about the ones in between? But I could say, okay, we could change the rules. So instead of all the numbers having to be different, what about if you could have repeats? Does that give you more options, less options? How does that change your maximum number? How does that change your minimum number? And all the while, what are you practicing? What do you have to do a lot of?
adding up, adding two-digit numbers. The usual way we get children to practice adding two-digit numbers is we give them an exercise in a book. This is what I call purposeful practice. Children want to do this because it has a point to it. So you remember you were saying, weren't you, they don't understand what the point of these things are. Well, okay, the point of this is to see if you can do a puzzle. It's not like saving the earth, but at least there is a point to it. But the thing that I'm most interested of all are the what-if questions. And those are the ones that children will ask of the class and of the teacher. Not what's the answer to something, but children coming up with possibilities of tweaking, of slightly changing this. So the children might say, well, what if you're allowed zeros? Or what if it's a 3x3 grid instead of a 2x2 grid? What if you're allowed fractions? What would happen if you were allowed negative numbers? By this time, some of the children have gone, I really don't care. But there will be some children in your class who will be hooked because they find this a really interesting problem. The mathematics is not difficult. The mathematics is really easy. But the questions that we are asking of it are quite sophisticated. A bit of reasoning. If I do this, if I make this go up a bit, I've got to make this come down a bit. Oh, this one's more important than this. So if I change this, it's going to make a bigger difference than this. So creating those chains of reasoning are really important, and that's what we want students to do. And what was my role? I didn't really do anything, did I? It's a really easy lesson for me. All I did was I posed a question, but every so often what I did was I brought together what you'd done and I formalised the things that you had found out. So if you'd been a child who was struggling, then at least you did hear an explanation from me, even if you hadn't heard it yourself. There's a professor in Cambridge, some of you may have heard of him, Ken Ruthven, very eminent maths education professor. And he says that one of the things that we usually do when we teach children in mathematics classes is we show them something. We show them a process, we show them a procedure, we show them how to solve a problem, and then we ask them to practice it. So they get really good at solving those sorts of problems. And what Ken says is, actually, how about letting the children do some exploration first? So that's what this was all about. It was about exploring, getting a sense of what things meant, constructing your own piece of knowledge about it. And then my job as a teacher was actually a much more difficult job than showing you how to do something. It was actually receiving what you said and feeding it back so that you understood what the argument was and what the story was. And then I asked you to find some more, and if we'd had time, I'd have given you more time to do it. So then you're consolidating your understanding of what's happened. So this problem is called Make 100, and it's on the Enrich website. And the URL of that, I can't remember if I put it at the end, but if you Google Enrich, nrich.maths.org, you'll get it. Okay. Have you all got a friend? Here. Have you all got somebody you can play a game with now? If you haven't, could you move to somebody who looks friendly? Perhaps you're sitting next to somebody who looks unfriendly and you want to move anyway. Okay. One of you, just one of you, I'd like to draw a line like this and put the numbers from 0 to 20 on it. And I was explaining to the teachers that I was working with yesterday, it's really interesting to watch the children do this, because we very often give them these, they don't very often write them for themselves. And you'll notice that they space out all the numbers along here, and then they realise as they get across the page that they've run out of space, so all these numbers get very squished together. And there's actually psychology which shows that children think that the space between smaller numbers is actually bigger than the space between bigger numbers. So they think between 7 and 8, the space is bigger than the space between 27 and 28. So there's some element of proportion going on there, which I think is really interesting. Okay, so we're going to play a game. As I said yesterday, I've given up telling my students the results, the rules of games, because they never remember them. So what I do now, in absolute silence, I show them the first 2 or 3 moves of a game, and they have to work out what's happening. Okay? So I'll tell you this is 2 people playing once against each other. Let's hope the animation works. Here's the first person's go. Here's the second person's go. Back to the first person. Back to the second person. Talk to the person next to you. What are the rules? I'll show you it once more so that you can work out whether you got the right answer or not. So here's the first person's go. Second person's go. Back to the first person. Back to the second person. So if we'd got time, we'd have a big class discussion about what the rules are, in the interest of speed. The first person writes a calculation which uses 3 numbers, 2 on the left, an equal sign, and the result of it on the right. And it could be an addition, sum, or a subtraction calculation. They're not, it looks as though it's addition, subtraction, but actually they could be all additions or all subtractions, whichever you like. And they cross off the 6, they cross off the 4, and they put a ring round the answer, which is the 10. Then the next person has to start their go with the ringed number. So they start with the 10, 10 take away 9 makes 1, cross off the 10, cross off the 9, ring the 1, back to the other person who has to start with the 1, etc. Does everybody understand the rules? So you're probably ready to play the game, except you don't know how you win. How do you think you win? Or how do you think you lose? By not being able to go. So if you can stop your partner being able to go, then you've won. Okay, have a go. See who wins. You circle it, and then you strike it. But if it's got a strike through it, you can't use it. Yeah. Has anybody got to the place where they've won? No. Once they've been scrapped, once they've had a line through them, you can't use them again. So usually at this point, I get a question which is, what do we do about 0? What do we do about 0? Can you use 0? How could you use 0? Well, if I tried to use 0 in the next line, it would be 18 plus 0 equals... 18. Can I do that? Yeah. No, because I'll have crossed 18 off. And the same is true if I do 18 subtract 0 equals 18. So actually, I should really have given you a number line that went from 1 to 20, but I want to give you something which makes you think. So the interesting thing about this game is, because you're grown-ups, you're talking to each other and telling each other what you're doing. When I do this in a classroom with children, the classroom is absolutely quiet. Why is it quiet? Because if you're trying to play a game against somebody and beat them, you don't want to tell them what you're doing, do you? Otherwise, they're going to know what you're doing. They're going to win. So in order to change it from a quiet activity to one where children are talking about their maths, I ask them to work in pairs to see if they can generate a list of calculations that crosses all the numbers off. So they're working together. And they spend some time doing that. And we get to the end of the lesson, and nobody's actually done it yet. So then I say, okay, nobody's done it. Does it mean that we're not very good at this? Because nobody's been able to do it? Or does it mean it's not possible? And I say to the children, right, well, take it home, play it with people at home, because it's a very easy game to play, you just need to do a number line. And then come back tomorrow and tell me if you've crossed them all off. And if you haven't crossed them all off, you've got to tell me why you can't cross them all off. So I don't give them the answer, I send them off. They're worried now, they've got something to really think about. I want them to be worried in a nice way. Can anybody tell me, apart from Ram, who's seen this before, can anybody tell me whether this is possible or not possible? Some of you really clever mathematicians. What do you reckon? Can you strike, except for 0, because we know you can't do that. Can you strike off every number? Or do you have to do it hundreds of times before you eventually can strike off every number? Is there a strategy that allows you to strike off every number? Or will you always get left with some? Interesting question, isn't it? We'll have a vote. Okay, you have to put your hand up either first or second, okay? Who thinks it is possible, given long enough to do it, to cross off every number on this line between 1 and 20? Who thinks it's possible? Two people, okay? Who thinks it's not possible? Okay, and the rest of you don't care. Sorry? You're worried taking it home. Good, I'm very glad. So I'm actually going to tell you the answer, which I never usually do, but I'm probably never going to see you again. So, here's the argument. On the first line, 6 plus 4 equals 10. How many numbers am I using? 3. Here's the 3. In the next line, I'm using 3 numbers, 10, 9, and 1. So that would be another 3, except I've already used the 10, so it's only another 2. So now I've used 5. On the next line, I will have used 7. On the next line, I will have used 9. If I generalize, I will have used 19. So can I ever cross off all 20? No. That's a proof which is perfectly accessible to primary children. It's a lovely introduction into making a statement which might sound outrageous, but actually they can confirm it. Yes, Ram? There are lots. And once, yeah. And the thing is that comes out of the children trying lots and lots of them, because then they start seeing some patterns and they start to generalize. So in a way, I'm shortchanging you with both of these activities because they're very rich activities that you can use to get a lot, depending on the age and stage of the children that you're working with. So both of these activities are what in Enrich we call low threshold, high ceiling. So threshold, you know, a threshold is the bit of the door that you have to walk over to get into a room. So we say these are low threshold activities. They're easy to get into. Yes?
So this argument says that because of your proof that there may be one number left behind, right?
Yes.
But to actually come up with a play that leaves exactly one behind is extremely hard.
Exactly,
Okay,
exactly.
so
that's
that's
the next bit. So this is a low threshold, high ceiling activity because everybody can start it so long as they've got some idea of adding up numbers and taking away numbers. They do loads and loads of practice of adding up and taking away number bonds to 20. Masses and masses of doing it because they're trying things out all the time. But there's a high ceiling because if you've got all of this adding up and taking away sorted out, you've got other things to think about, which is in the line of generality and a bit of proof. So, we were talking about how do you in a class where you've got very mixed ability classes, how can you possibly let children all do the same thing? Low threshold, high ceiling activities are one of the answers to that. You can give this to everybody in the class and everybody will have something that they can do. Rather than accelerating students through to new content, it's asking them to do a different, more sophisticated form of reasoning. And if you do things as a class, then it helps the class to feel as they are a community of inquiry. So they're not doing mathematics completely by themselves. And there is the URL, enrich.maths.org, and that last activity is called Strike It Out. I'm now going to hand over to Rachel, who's going to finish off. Thank you for being a very good class.
Okay, we are already over time, so I'm not going to speak for the full amount of time because I think that's been much more interesting than listening to me speak. I'm going to briefly tell you about a little bit more about the project and also how you can start to get involved. So we've already talked about, we are a research project. We're backed by the University in Cambridge, so we work with the Faculty of Education, the Faculty of Maths, Cambridge Assessment and Cambridge University Press. So all of those groups funded the project and they decided that they wanted to do something innovative, something that looked at using modern technology and something that could be of use to the world at large. So a lot of what we're doing now will be publicly available for everybody to use. It's not going to be behind a paywall. The aim is, that's the team, that's some of the team. So we're not a big team. We've got a lot to do, but we're not a big team. But we've all got backgrounds in education. We've all been teachers in some guise or another, and then we've all been involved in curriculum development, in research, and other areas of maths education. What we're looking at is to build a framework, which I showed you a picture of, for age 3 to 19. I'm going to leave you to have a look at the website because we've got an aeroplane to catch, so I don't want to miss my flight. But it's worth having a look on the website, which is cambridgemaths.org, and that'll give you a lot more information about the ideas behind the project. I showed you earlier the diagrams that we've been working with, and to give you a slight idea, that's a little bit what all of it looks like, although that was taken about 6 months ago. So if you can imagine about double that size now, and for every one of those places, we've got what the mathematics is, why the mathematics is important, and these different ideas about entry. But we've also got bigger collections, so we've been starting to look at what we call pervasive ideas. So what are the things that pervade all of the areas of mathematics? What's the place of proof? What's the place of symmetry? All of these different ideas are also connected in there. Now, what we talked about was just the mathematical layer and the connections between the mathematics. And again, that's all connected to the research as well. So if you imagine that middle layer there as the mathematics layer, what we're also doing is connecting in the research base. But we're also now starting to think about, well, what else can we do? What are the kinds of activities that draw things together? So things like the Enrich activities, we're starting to think, if you take an Enrich activity, where would it map to on this mathematical content? If you take a different type of activity, where will that match to? So eventually you'll be able to go from an activity to look at the mathematics involved, or you'll be able to pick a piece of mathematics and go to some really interesting activities that really develop this mathematical thinking and maybe the mathematization that Professor Ramjan was talking about. Other things we've been looking at is developing professional development for teachers based around this as well. One of the reasons I'm involved in the project is I worked a lot with primary teachers who were scared of maths, and they were nervous to do the kind of activity that Lynn just did because they didn't know what would happen. They weren't confident themselves in the subject matter. So one of the things I would like to do is see this being used for teachers to support them in their understanding of the mathematics and how it fitted into the bigger picture. We are constantly, we're constantly looking for people to be involved in the project in terms of giving us consultation and giving us their opinions of testing out things. And there are 3 ways you can really get involved at the moment. If you go to the website, we produce research papers that are called espressos, and we're always looking for people to collaborate with those on. We're looking for questions about mathematics that are worth investigating. And the researcher Lucy, who puts those together, looks at the recent research in that particular problem area of maths or of the classroom and puts together a double-sided sheet that's really about how this affects the classroom, the implications for the classroom. The other place you can look at is in the blogs. And there is a whole selection of those, but we invite people to read those. Some of those are philosophical ideas about mathematics. Some of them are very classroom-based with ideas about teaching. But we're always looking for people to comment on those and people to trial out the activities. The last thing you can do is on the website as well, you have an area where you can join up with the newsletter. And if you do that, you'll get regular updates. And those indicate times in the future also where we'll be looking for people to read through some of the things I've been talking about, so the research summaries and things like that, and also to collaborate on espressos, or even if there's people interested in reading some of the blogs, I'd be fascinated to maybe collaborate on a blog about geometry, so about the columns or the Rangoli patterns, and have a look at those. It'd be really good for me to be able to liaise with somebody. So the best thing I can do is have a look at the website and have a look at those espressos and the blogs and sign up for the newsletter. I'm going to pass now to Ratnesh, who's going to just do the final closing remarks. You don't need that, do you?